Okay, so in this last video, we're gonna just look at how the electric potential looks like graphically, and look at some like two-dimensional plots to try to like understand it better. And I've got a little simulation that I'll show you at the end that will hopefully like help tie it together with electric field. Okay, so before we start looking at the pictures of potential, let's just go back over the basic example that we went through in the last video, which is like, let's say we have a positive charge Q, and we want to know like what is the electric potential at this point, some distance r away from it. Okay, so to calculate the potential at that point, we would just divide Q by R, right? And I mean, if we wanted to sort of like, and K is just a constant and Q is just the charge, so which is constant also. So if we wanted to sort of look at what that function looked like what the potential looked like as a function of like the distance from the charge, the function would just look like this, right? Where as you go away from the charge, as the distance increases away from the charge, the potential drops. Okay, so this is like a 1/r relationship. Okay, and so if we were to try to map what that potential would look like in space, like in two-dimensional space, it would look like this. Like it would go off in like all directions, right? Like all it would be like a contour like this, right? Where the charge, the positive Q charge would be like here, like kind of in the middle of, oops, let me draw that better. In the middle of this shape, right? You'd have like the charge, right? And then as you go away from the charge, so this would be like R. Like as you go away from the charge, the potential gets smaller and smaller and smaller. Okay, like what we see in this function here. Okay, so basically this function is just these green contour maps are the same as this function 1/r, but like plotted, like everywhere in space. Okay. And yeah, I mean something to notice is that as you go out from the charge, I mean like if you look at the function, um, when you're right on top of the charge, so if r equals 0, the function blows up, right? It goes to infinity. So like as in the limit of like r going to 0, then v goes to like infinity. Okay, so like that's kind of what we see here. Like it goes there's like an asymptote. It goes very, very high, like as you get closer to the charge. If we wanted to plot what like a negative charge would look like, it's the same, it's exact same idea, except it's like pointing in the opposite direction. So if I were to plot like V as a function of R, it would just look like this, right? It would be negative Q over R. Um, the thing to notice is that like as you get closer to R, the function gets like steeper and steeper and steeper, right? And it's not a linear relationship as you can see like in this plot here. Okay, so like another way to look at this is if we were to try to project the potential onto um like a one-dimensional plot. Okay, so like this picture here, this green contour is exactly the same as what I've drawn, what we've drawn here. It's just bigger. But the point that we're trying to make here is that like each of these like contours, and like so here's a contour, here's another contour, here's another contour, right? All of these are at like set potentials. So like let's say this is a potential, this is potential 1. This is potential 2. This is potential 3, potential 4, potential 5, and so on, potential 6. Each of these could be like projected onto this plot, right? So this would be like that line there is potential 1. This would be potential 2, and so on. The important thing to realize here is that um, all the way along this path and all the way along this line, because it's the same thing, it's just different representations of the same thing, the potential is the same, like all the way around those contours. Each contour is at the same potential. So what we call these contours are equipotentials. Okay, so it's an equipotential line. So like let's say this was at like 15 volts, then it wouldn't matter like if I was here or here or here or here or here. Like I could put a charge in any of those spots and it would still experience the same potential of 15 volts. Okay. Another way to look at this is I could move a charge. Let's say I had a little test charge and I put it on this contour line. I could move this charge from here to here to here without doing any work. No electric work needs to be done to move a charge along an equipotential line. Okay, so that's super, that comes up later. That's super important. Equipotential line, you can move a charge all the way like along it and no work. There's like zero work needs to be done because it's everything on that line is at the same potential. Okay, another thing to sort of like realize, and this comes up in one of the problems on the last problem on the challenge, is that if you have a surface, let's say you have like a conducting surface, this is a conductor, okay, and this conductor has like a specific potential, like let's say it's charged, like everywhere on that surface is going to be at the same potential. So by definition, a conducting surface is an equipotential. Okay, so let me write that down here. Conducting conductors are equipotential surfaces. And the reason for that is simply that the charges in a conductor are free to move around. And so they move around in such a way that an electrostatic equilibrium is reached very, very quickly. And the entire surface is at the same potential. So like you could have a surface and you could move, let's say like you put a charge like on the surface, you could move that charge like anywhere on the surface without doing any work because everywhere on that surface is the same potential. Another thing to realize, and this maybe came up when you were building your electroscope, is if you have a conductor, like let's say I have a conductor, a conducting surface, and I connect it to the ground, like I ground it, then by definition, that conductor is at a potential of 0 volts, which is the same like potential as the ground. Okay, so like if I connect a conducting surface to the ground, it's by definition at 0 volts. Okay, you've grounded it. Okay. So those are two sort of like important points. And let me just to finish off here. Let me share another screen. Just one second. Screen. Okay. So this is the fat simulation that I showed you a couple of weeks ago, but we're going to come back to it just because it's a nice visualization for electric potentials. So to get to it, it's the same link as I shared before. It's just like if you just Google FET simulation electric field, this will come up. So we're just going to play around with this. I'm just going to talk through a couple things. So I've shown this before, like I put a positive charge somewhere in space, and you can see the electric field lines radiating outward from the positive charge, like out to some distant point in infinity. I can use this little tool here to map out like the potential lines at each of these points. Okay, so like this is kind of just like a plotter. Actually, let me remove the electric field lines for now. Just we'll come back to that. Okay, for now, I'm just gonna like ask this little tool to plot electric potential lines, equipotential lines. Okay, so like there is one. I mean, you can put them wherever you want. And I recommend that you mess around with this a little bit yourself. It's kind of a fun tool, and it's like it's very so I've tried to put them like approximately equal spacing from each other. But what you realize is that the values, like the voltage values, are not going down linearly. And that's simply because of that 1/r relationship that we saw on the previous slide. Okay, so that's a cool thing. The uh, the electric field lines always point, and I said this in the other video, but I think here you can see it really nicely. The electric field lines always point from areas of high potential to areas of low potential. So here I'm very close to the positive charge. I've got a high potential. By the way, this is an equipotential line. Everywhere along this line is 21.6 volts. Okay, so I could put a little charge here, and I could move it like all the way around this equipotential line, and like I wouldn't have to do any work. It's at the same potential. Same thing here. I could move like to my heart's content all the way around this 11.7 volts, no work. Okay, but to move it from like here to here, I would have to do work. Well, the field would do work, right? I mean, and I talked about that in the first video, right? And let's say I had like a positive charge and I put it at this 11.7 volt. And let me put the electric field lines on there. So like, let's say I have a little positive charge and I put it here at like 11.7 volts, which is like a lower potential. And I push it towards this positive charge. The electric field would be doing negative work on that charge, right? This is coming back to the very first video where, because I'm pushing it like in this direction, but the electric field is pointing out, right? So it's going to be negative work, but I would be increasing the potential energy of that positive charge by like moving it closer to the positive charge that's creating the field. Okay. So yeah, so here you can see that the electric field lines point from areas of high potential to areas of low potential. Let's see like what happens if I put a negative test, or I put a negative charge there. Okay. So it's going to be the exact same thing, but just opposite, right? So if I put an equipotential line here, that's going to be negative 17, right? Negative 8, negative 5. I'm trying to like space them relatively evenly. Okay, and then so it's the same kind of like 1/r like drop off, but it's just negative values now. And then I put the electric field. So here you can see that our rule of the electric field line still going from high potential to low potential is still like honored, right? Because the electric field, which are these like fat arrows, are pointing from areas of relative high potential to areas of relative low potential. And same deal, like each of these green lines represents an equipotential line. Okay, that's pretty much like all I wanted to do in this video.